So this course deals with physics. And what I often find is that students walk into this class not really knowing what physics is. They can't put a finger on what the word physics even represents. If I ask you what biology is, usually people have absolutely no problem defining that there. It's the study of life. Right? If I ask you what, you know, psychology is, they tell you, oh, that's easy. It's the study of the mind, right? But if I ask you what physics is, people usually pause. They're like, I don't know. It's the study of something. And the reason that it's difficult to put your finger on what exactly physics is because physics is that branch of science that is so fundamental that it underpins literally everything. Um, I like to think of it sort of as an analogy. If I ask a person if they understand computers, the answer you get depends a lot on what someone thinks you mean when you say, "Do you know about computers?" Uh, in case in point, my mom. God bless her. My mom is really old, and old people tend to be technologically challenged. But she's gotten pretty good at using her computer to get online and get on Facebook and share photos, and she knows how to do all of that stuff. If she wanted to write a letter, she knows how to open up a Word document and format it and do all those sorts of things. So to that extent, she understands computers in that she knows how to do that set of tasks and to navigate around like certain kinds of software programs that she's familiar with. That's if you ask about does she know computers, absolutely, she knows that. That's one level of understanding how computers might work. Um, Now, that's not the deepest level, though. There are other people who, when they deal with computers, they deal with it on the level of actually writing programs. They create the programs that other people then interact with. That's another layer of understanding computers. And you can spend uh, a whole lot of time on either of those two levels, right? There are people who may be super, super experts in how to make Adobe Photoshop work. Um, and there may be people who write programs who've never used Photoshop and don't understand how Photoshop works. So you can be an expert in the sort of software level of knowing computers, or you could be an expert in the programming level of knowing computers. And you could spend a lifetime gaining expertise in either of those two fields. There's another level of understanding what a computer is, and that's the hardware level. Like when I hit the A key on my keyboard, I know that that pops up the letter A on my screen, but what's really happening? Well, I'm mechanically depressing a key. That key decreases the space between two plates on a capacitor, and that changes the size of the voltage between those two things, which then draws more or less current out of some element of your machine, and that sends signals that get encoded into little bits of binary. And so there's a whole hardware level of what's going on, of understanding what a computer is. And there are people who know how to write programs, but they don't know how to build an integrated circuit. They don't know what chips go where, and they don't have to. So there's a whole other level of understanding computers that's kind of the underlying base level. And if you were a person who was studying one of those three fields, sometimes it's helpful in your field to know a little bit about what's going on in one of the other fields. So for instance, if I was a person who was writing programs for a living, but I understood like what was mechanically happening in the chipset or on the motherboard of my computer, I might be able to write programs that run more efficiently. If I'm a person who is utilizing some piece of software, it might help me to make that software run better if I know certain amounts of basic scripting, right? The fact that I can do a little bit of programming means I'm actually better at running Excel than someone who's never written a program in their life. So sometimes there's a degree of crossover between those three layers of understanding. Now, why am I talking about this? Well, to understand what physics is, it helps think about it in terms of that analogy. So when you think about science and the study of nature in general, there's different levels of understanding. And one way to think about it is that physics is like the basic hardware of the universe. By studying physics, we're kind of learning how the universe works on the same level that we might understand like how the integrated circuits and how the keys and such work on a hardware level in your computer. When you think about chemistry is kind of like the software level of understanding the universe. You're learning rules about how different atoms interact and form molecules. You learn about how they can exchange electrons, and those sorts of things can cause them to bond into more and more complex compounds. But at the end of the day, the reason those rules exist, the reason that chemistry exists, is because of the interactions of basic physics. And in fact, if you are chemistry majors, which many of you are, you'll go on to take physical chemistry, where you're going to start to see much, much more specifically how the stuff we'll learn in this class influences the laws of chemistry that you guys probably learned in high school, or at very least freshman year. At the end of the day, all the laws of chemistry are in fact laws of physics. And then of course, you guys are mostly biology majors. You can think of biology as kind of like that software level. Like you can spend an entire lifetime thinking about how life forms interact. Ecology doesn't require a great deal of knowledge of chemistry. People who were biologists in Darwin's era didn't have to do a whole lot of math, but to understand those things on a more complex level, you often have to dive down and look at the chemical interactions that happen in a life form. You learn about things like the Krebs cycle and respiration and all that stuff. So in a way, sufficiently complicated systems become biological systems, and you can think of biology as being just really, really advanced chemistry, which is why all you guys who are getting biology degrees end up walking out of here with a minor in chemistry by default, because you have to understand that next layer down to really get a full appreciation of that top layer. So that's kind of what physics is. Physics is a basic study of the most fundamental interactions of matter and energy. And since everything in the universe is made out of matter and energy, physics shows up everywhere. But because that's so broad, we have to break that down into manageable chunks. And so physics has several branches. The branch that we're going to spend our time learning this semester is a branch of physics called mechanics. Let me switch on my screen share so I can write stuff down. Hitting the button. That's not the camera I want. That's the camera I want. So the branch of physics that we're dealing with this semester is mechanics. And mechanics is about how objects move around. We often think of mechanics as the study of motion. Now, there are plenty of other branches of physics, and you're going to spend a good chunk of time learning several of those. Next semester, we're going to learn a second branch of physics called electrodynamics. Electrodynamics is about electricity and magnetism. And of course, we end up having to learn this second because many of the rules of electricity and magnetism are themselves derived from laws of mechanics. Probably similarly important is thermodynamics. That's a branch of physics that we don't spend a lot of time on in the physics sequence, but you end up learning a lot of thermodynamics in your chemistry courses. A lot of what you learn in chemistry 1 is really physics. You'll also spend, if you take physical chemistry 1 is all about thermodynamics. But this is how heat and temperature. So that's going to get the short shrift. We're not going to spend much time on that in physics 1 or 2, but you'll see that a lot in GChem. You see it in physical chemistry. That's where you learn all that stuff if you're a JCSU. The other big branch of physics is quantum mechanics. And it's the study of motion of sorts, but it's very small things. Turns out, if you're super, super tiny, by which I mean things on the scale of atoms or even individual protons or electrons, they obey different rules. And so the laws of mechanics are more complicated for those tiny things. You learn a little bit of that in general chemistry. You'll learn a little bit of that in physical chemistry too. And we'll touch on some things, but not very much in this course. We're going to be mostly dealing with large macroscopic things, things that you could see with the naked eye. And their motion is pretty straightforward. And then I should probably call out optics, which is light. We're going to spend a good chunk of time on optics next semester. And technically, optics is a special case of electrodynamics because at the end of the day, light is just an electromagnetic disturbance. So we have to understand this stuff before we can understand this stuff. So those are the big branches of physics. And even within those, there are subfields. And in fact, this semester, mechanics is going to have 2 subfields. There's a reason I left all this space. We're going to spend a couple of chapters learning something called kinematics. And kinematics is just where we're going to learn how to describe an object that's moving. We're going to have to be able to describe what's happening as objects move around in enough level of detail that we can sort of parse what's going on. And so that's where we develop the vocabulary for even talking about the moving objects. So this is just the description of motion. But when we talk about kinematics, we don't really care why things are moving the way they're moving. We're just trying to describe what is. So the next big branch of mechanics is called dynamics. And that's where we start to look at why is it moving in that manner. We start looking at what the fundamental causes of the motion are, what the fundamental changes in the motion are resulting from. And that's going to be the 2 big divisions in this course. We're going to spend the first couple of chapters just getting the vocabulary required to describe things that are moving. And then we're going to shift gears once we can describe things adequately. And we're going to bust it down and look at why is it moving that way? What sort of things affect the motion of an object? And that's where we're going to be spending all of our time this semester. Next semester, we're going to hit these 2 things in physics 2. And then these things here you guys get in either chemistry or GChem. So it's all stuff you'll end up seeing to one degree or another. But that's kind of the basic overview of what physics is. And you'll notice this is a really broad bunch of stuff. I mean, we're going to spend a lot of time talking about things sliding down ramps or things being dragged across the floor, big objects moving around over here. And that looks totally, completely different from, shining lights on stuff or watching heat move around. Physics is such a broad category of things that it's really hard to pin down because at the end of the day, everything is physics. It's everywhere. And there's no part of your life that is not informed at least a little bit by the study of physics. Awesome. Any questions? You guys okay with this? All right. So let's get started. Let's talk about.
I have a quick question, Professor.
Yes, Abigail, what do you got?
Are you gonna send us the paper? I'm not really writing down all of it.
Am I
Are you
going to
saying that
send you?
the material, the one you just write it down?
Oh, like this, you mean?
Yes.
Uh, I mean, I'm going to post this video. This
Oh,
video
okay.
is
Okay.
let's make sure that I hit record. I did.
Okay.
Hang on.
Yeah,
Now I'm starting to concern myself that I didn't hit the record button.
you are recording. So if you upload
Okay.
the recording, I can.
Right. What will happen is it's being recorded in the cloud. Usually about an hour or so after the class ends,
Mm-hmm.
Zoom will finish processing it. If you look in your Zoom window, and come on, if you look in your, let's switch shares. I can show you what that looks like. Screen share. Boom. So if you look in Canvas, what should happen if you go to your Zoom window, you'll see a, come on, let's load, buddy. There we go. You'll see cloud recordings, and it'll start to show up here.
Okay.
What I found is that there's not a whole lot of space, so I tend to migrate them pretty quickly to a YouTube channel. So
Okay.
once I download this and put it on the YouTube channel, I will then post it, and you'll find them after they've migrated under this heading here in Canvas.
Class video. Okay, got it. Thank you,
So
Professor.
if you don't see a post here, it means it has been migrated, but it should be in the other spot. So yeah,
Okay,
all
thank
these
you.
videos are around. You can review them at your leisure. People who couldn't be here while recording live can get them there because online classes are weird. Everything's asynchronous, and I can't count on people being available reliably during the normal class meeting windows. So that's where
Okay.
you'll get all this stuff.
All right.
All right. So far, so good.
Yes, we are. Thank you.
Awesome. So let's learn how to do some kinematics. And in order for us to do kinematics, we're going to have to learn how to describe objects that are moving around. And we're going to have to develop the vocabulary for expressing, where things are, how they're moving, what nature of motion they're undergoing. And that's non-trivial. A lot of you who haven't taken a physics class before probably haven't had to think very hard about how to describe a moving object. So let's talk about that. What sort of things am I going to have to specify in order to describe the motion of an object? Well, let's start with a simple picture. So here's the ground. I'm going to draw a stupid tree. That's a tree. I failed art class and had to go into physics, so my drawings will uniformly be terrible. Over here, here's a dude. Over here, here's another dude. Over here is yet a third dude. I got a tree and a bunch of people. And what I would like to do is describe like where each of those people is. So if I asked you to describe the position of this guy right here, how would you do it?
Can you name the guys like A, B, C so we can tell you like?
Yeah, I'll call him person 1, this guy person 2, and this guy person 3. So what is the position of person 2?
The right side of the tree?
Perfect. That's a description of where the person is. He said, person 2 is to the right side of the tree. Now, how is that different from person 3? How is the position of person 3 different from person 2? Because they're both on the right side of the tree, right?
The distance between the tree, the second person and third person.
Yeah, so you could always, you could distinguish between the positions of these two people by noting that this guy over here is further away from the tree than this guy is. Now, the thing that I want to point out here, and I could be pretty well guaranteed you were going to do it, is that as soon as somebody tries to describe the position of one of those people, they always ended up having to do it by referring to some other object, right? Where is person two? He's to the right of the tree. They weren't able to talk about where person two was without referring to something other than person two, like the tree. And that's true in general. No matter how hard you try, you cannot describe the position of an object without referring to some other object. If I ask you, hey, sweetheart, where's my, my lucky pair of pants? Oh, Tom, it's in the washer, right? I'm looking for a bowl of cereal. Where's all the cereal? The cereal is in the pantry, right? So I'm referring to the position of something, the cereal, in reference to another object, in this case, the pantry, right? Try as you hard, you can't do it. Where's my book? It's on the shelf. Where's my dog? He's on the floor, right? So every time you refer to an object, you always end up referring to it in reference to some other object. So in physics, we're going to formalize that process, and we're going to call that choosing a frame of reference. And it's going to be helpful to us to always be aware of what our frame of reference is. So when we were describing the location of person two and person three, we were doing it by using the tree as our frame of reference. We were always referring their positions relative to the tree. Fair enough? Now, bear in mind, there's nothing special about that tree. I don't have to use the tree as my frame of reference. I could have said that person two is to the left of person three. So I could have chosen person three's location as my frame of reference. Right? So when you choose a frame of reference, you could choose anything. You could even describe the position of an object in terms of a frame of reference that is itself in motion. So like if I'm driving down the road and I've got my coffee cup in the cup holder, right? And I want to know the position of my coffee cup. I could say, oh, my coffee cup is in the cup holder. So my frame of reference would be the cup holder, and the cup would be the object that I'm referring to. Except if I'm driving down the road, the cup holder itself is moving with my car. The cup holder is moving. If I asked you where my coffee cup was and I used my house as a frame of reference, then what would happen is at one moment, the coffee cup would be a certain distance from my house. And a moment later, it would be even further from my house because the entire cup holder and the car with it has moved. So you could even have frames of reference that are themselves moving around. So anytime we start describing the position of an object, we're always going to describe the position in terms of a chosen frame of reference. And if we want to describe that position as precisely as possible, position will always be a distance. It's going to have units of length. In a way, the easiest way to choose a frame of reference is...
Professor?
Yes, ma'am.
You kind of breaking up sometimes. It's not really clear.
Okay, hang on. Let me see if I can't. All right, I'm gonna change microphones and see if that helps. All right, how's the audio quality now? Has it changed?
We see the water wave.
I'm sorry?
there is a noise, a background. There is a background noise.
Right, I think that was the case. That's why I was using the other microphone. Hang on, let me test the speaker and microphone. Works, yes. All right, I'm making a noise, and I'm making more noise, and I'm making more noise. Okay. All right, so that's the Lumens microphone. Let me change the other mic. Nope. Yes. All right, let me swap the other mic.
All right, testing 1, 2, 3, testing 1, 2, 3.
That sounds better.
Okay, okay. If it gets bad again, I may pull my headset out and try that instead. Weird. All right. So, lost your train of thought. Let's go back to that. All right. So when we're choosing a frame of reference, we'll make a specific choice about where we're going to refer to. Let's, for this case here, let's use as my frame of reference my tree. Let's use the tree as my frame of reference. And what's going to happen is we're going to start out simple in this class. Chapter 2 is a chapter on one-dimensional kinematics. In other words, we're only going to be considering the motion of an object along a straight line. In chapter 3, we'll relax that restriction and we'll start to let things move in like more complicated paths. And it'll be more difficult to specify the position of an object in 2 or more dimensions. But in 1 dimension, it's easy because all I got to worry about if I'm only moving along a single line is I can measure the distance from the tree along that line. It's like choosing an x-axis. And therefore, I might call my tree x equals 0 because how far is the tree from itself? It is 0 meters from itself. And person 2, maybe he is 3 meters to the right of the tree, and maybe this guy here is 5 meters to the right of person 2, and maybe this guy over here is 3 meters to the left of the tree. And so I could describe the positions of person 1, 2, and 3 using this frame of reference. I would say the position of person 2 would be, I'll call it x2. That would be x2 equals what?
Three
3 meters, right? Notice positions have units, and units are important. Now, what about the position of person 3?
Three plus 5.
There you go. He is a total of 8 meters from the tree, so I would say that his position would be x equals 8 meters. Now, I've picked this one last for a reason. What's the position of person number 1?
The distance is 3, but -3.
Yeah, and that's the problem, right? I don't want to say that he's at x equals 3 meters because that would suggest he's in the same position as person 2, which is clearly not true. So when we're talking about positions, it turns out positions could be negative, right? That makes sense. If this is x equals 0 and the numbers are getting bigger as I go to the right, then going to the left is just going to be a change in the opposite direction. So I could specify his position as being -3 meters. And so what we realize is that the plus or minus is just going to be a way of including a direction. By choosing this frame of reference, any kind of positive position is going to be to the right of my tree, and any kind of negative position would just be that same distance, but to the left of my tree. So position could be positive or negative depending on what frame of reference we've chosen, and also depending on what direction the object is. All right, super easy, right? We can do this in our sleep. Let's make it more complicated. Let's let some objects move around. Now, I wish I had a bigger thing for this. I want to keep that picture to refer to. I'd like to have person 2 walk over and talk to person 3. And what I'm interested in tracking right now is a quantity that we call displacement. And displacement is defined very simply as the change in an object's position. So person 2 goes to stand with person 3. What is that person's displacement?
One more question. I mean, can you repeat the question, please?
Yes. So displacement is change in position. And so I want person 2 to travel and stand with person 3. And I want to figure out what his displacement would be.
5.
5 meters, right? He has to change his position from x equals 3 to x equals 8. That's a change of 5. And in fact, you know, elementary school math tells you how to calculate that, right? Change in position, that would be delta x. Remember, delta means change. And that would be his final position minus his initial position, which in this case is pretty obvious because he ended up at this location at x equals 8 minus his original position, which was x equals 3. And lo and behold, that is the quite obvious from the picture 5 meters. Yay, super easy. Now, by that same reasoning, person 1 goes to stand with person 2. What would person 1's displacement be?
Mm. 6.
Yeah, because same idea. He's traveling from x equals -3 to x equals +3. So he's going to travel, you can see kind of visually, 6 meters, 3 plus 3. You could do it mathematically the same kind of way. His final position was 3 minus his original position, -3. But minus and minus is the same as a plus. So that person would have a displacement of 6 meters. All right, person 3 goes to hang out with person 1. What is his displacement?
Eight plus 3. 11.
That is close, but not quite correct.
You said person 3 goes to person 1.
Person 3 travels to stand with person 1. So when she said 11, and she's not wrong to think about it this way, she's like, look, he's got to go 8 meters to get to the tree, and then another 3 meters to get to the person. So 8 plus 3 is for sure 11. And yet that's not the right answer. And the reason it's not the right answer, if you think about it this way, is that if I'm doing delta x as final minus initial, his final position was -3, right? Minus his initial position, which was +8. That's a displacement of -11 meters. Does that make sense?
Yes.
Now, why is it negative? Well, again, what that minus sign is representing is a direction. Because person 3 was traveling to the left, right? If this person had a displacement of 11 meters, positive 11, he'd be traveling 11 meters to the right. He would end up even further from the tree. But instead, he's traveling to the left, and that's why his displacement was negative. So displacement can be positive or negative, And the sign just refers to the direction. These two were both positive because in each of those examples, the person was moving from where they started to the right. So they had a positive displacement. But when I move them to the left, I have a negative displacement. So the sign is just our way of keeping track of what direction things are moving. Now, there is a similar but distinct term that will sometimes get thrown around. And one of the things that you're going to have to watch for in this class is nuance, right? A lot of times what will happen is we will have certain words that we'll throw around that mean something very specific. And sometimes I'm choosing my words exceptionally carefully because I want to mean one specific thing rather than some other similar but not quite the same thing. And one of the terms you're going to have to wrestle with is the distinction between the term displacement and the related term distance. Now, distance is just the magnitude of the displacement. All right. By definition, distances cannot be negative. Right? They are by definition positive. So had I gone back and said, hey, person 3 goes to travel next to person 1, what distance do they travel? The answer to that question would have been 11. They went 11 meters because displacement may care about whether you're going to the right or to the left. Distance doesn't care about what direction you're traveling. It's always adding up no matter what direction you're going. It's kind of like, think about the odometer in your car where it measures your mileage, right? Whether you're driving to the north or you're driving to the south, your odometer is ticking up. So if I take a trip from here to Raleigh, I'm going to drive to the east a certain number of miles and my odometer is going to tick up. When I drive back to my house, the odometer is not going to roll backwards to go back to the same number of miles I started with. It's going to tick back up the same amount when I drive back to Charlotte. So distance always accrues. Displacement, however, does not necessarily always accrue. I could have a positive displacement followed by a negative displacement. Does that make sense? So imagine that the following occurs. All right, person 1 has an argument with person 3. So he walks over to person 3, punches him in the face. Then he travels to person 2, says some bad words to him, travels back to person 3, punches him in the face again, and then goes back to where he started. So from here to here to here to here. What's the displacement of person 1 over that trip? Person 1's just a jerk.
What was the question again? Sorry.
So here's the scenario. Person 1 travels over to person 3, punches him in the face, travels back to person 2, says some nasty things to him, then decides he's not done punching person 3, goes back to person 3, punches him some more, and then goes back to where he started. So what's his displacement over that entire trip?
0.
0. That's exactly right. Why is it 0? Because he began and ended in the same location. His total displacement was 0. For every positive displacement he had when he traveled to the right, there was another moment during that trip where he was traveling to the left the same amount, and they all ended up canceling out. So his total displacement was 0. And that's always going to be true if you begin and end in the same location. Now, the distance that he traveled was clearly not 0. He went 11 meters, then 5 more for a total of 16, then 5 more for a total of 21, then 11 more for a total of 37. So he traveled 37 meters of distance, but still had a displacement of 0. So far, so good? So That's the concepts of displacement and distance. They are obviously related. They're both measured in meters. They have the same units, but they are distinct. And pay attention in questions to which one you are being asked, because sometimes there's a subtlety there. Now, when we're dealing with things moving around, how far they've moved is not the whole story. In terms of tracking how things move, it also matters like how fast you're moving. But when I say that something is moving fast, what does that even mean? What does it mean to move fast versus moving slow?
Maybe depend on the weight.
Well, it turns out that the weight might matter in terms of how difficult it is to make something move fast. Like a heavy thing might be more difficult to make it go fast than to go slow. But remember, this is kinematics, and we don't care why it's traveling at that speed. We care about just describing it. So the weight won't even matter until we start talking about dynamics in chapter 4. So it's not that. What does it mean when I say something is traveling fast? What do I mean when I say it's traveling slow? They're words you clearly know the definitions of because you speak English, but it's sometimes hard to parse what's going on, and that's what we're going to have to do is to quantify all these things that seem super easy.
The distance really matter?
Well, sort of. Imagine that person 1 travels to person 3, right? But he does so slowly. And imagine that person 1 has a twin brother in the same location who also travels to person 3, but that person travels fast. Now, in either case, the distance being covered is the same for both, right? They're both going to have to travel a total of 11 meters to the right. What's different about the person doing it fast compared to the person doing it slow?
Oh, time?
Time. How long it takes for them to get there, right? That when we talk about speed or how fast or slow something is, the distance is only part of the issue. The other part is how long it takes. A person who's traveling fast is going to cover that amount of ground in less time than a person who is traveling slowly. So that's where we're going to introduce the concept of velocity, right? And velocity is going to be defined as the rate of change in position. Now, what do I mean by a rate? Well, that term rate is again another one of those terms you guys certainly know, but maybe can't pin down exactly what it is. But when you talk about rates, it's always something per something. So like if I'm traveling to Europe and I want to convert my dollars into euros, right? There's an exchange rate. We'll give you this many euros per dollar that you give us. If I get a job and I'm working at an hourly rate, I get paid a certain number of dollars per hour that I work. So rate is always a ratio of something over something. And in this case, it's going to be a rate of how far you've traveled per amount of time it takes to make that travel. In other words, we're going to define the velocity as being the change in your position. Oh, wait, that's the displacement divided by the amount of time that has to pass in order for that change in position to occur. So if person 1 was traveling to go travel next to person 3, the change in position was going to be 11 meters no matter what. But if they're traveling quickly, then the time that it would pass would be smaller, and that would result in a larger velocity. If they were traveling slowly, they'd have that same 11-meter displacement, but the time it would take would be much larger. They'd be dividing by a bigger number and therefore have a lower velocity. That's what it means. And that's why we measure velocities in things like miles per hour, right? Meters per second, right? It's always going to be a distance over a time. Super easy. Now, does it make sense for a velocity to be a negative number? Could I have a negative velocity?
I would say no because time cannot be negative.
That's certainly true. There is no way that the bottom of this fraction could ever be negative, because if that were the case, I would have to arrive at my destination at an earlier time than when I left. That's crazy, right? Unless you have like Marty McFly's time machine, that's not going to happen. So this can't be negative ever. But what about the numerator of that fraction? Could the numerator of that fraction be negative?
Can't.
You sure?
Yes, yes, 11 can be. Yeah, can be negative.
Yeah. If person 3 travels to person 1 and it takes him, let's say, 5 seconds to make that trip, well, his displacement was negative 11. So negative 11 over 5 would be negative 5.5 meters per second. So yeah, velocity can totally be negative. And what's that minus sign telling me? The direction. Because this dude was traveling in the negative direction, so he has a negative velocity. If I was traveling in the positive direction, that would give me a positive velocity. So what you're going to find is happening over and over and over again is the pluses and minuses are just a way for us to keep track of left and right, or up and down, what direction we're going. So velocity can absolutely be negative. And in fact, when I talk about a velocity, it's important to remember that I need both elements of information. I need to know the number part, but the sign is equally important. Velocity has both a magnitude and a direction. That's important because if I ask you in a problem to say, find the velocity of so-and-so, right? If your answer to that question is 5.5, that is not a complete answer. 5.5 is a magnitude. It's a number. He's going 5.5 meters per second. But what I would need in addition to that is also the direction. Oh, he's traveling 5.5 meters per second to the left or to the right. And that's to the left or to the right you would get by looking at the sign of your answer. Now, just like displacement and distance are related but distinct, in physics, velocity is related to speed, but they are distinct. They are not quite the same. In casual conversation, you might use these two terms interchangeably, but in physics, that'll get you in trouble because speed is the magnitude of your velocity. And again, what do I mean when I say magnitude? Sometimes I see students get really kind of thrown off by this word magnitude because they think that it's like some kind of weird physics jargon part, but really it just means the number part, right? So by definition, anything magnitudes must be positive. So if I said person 3 travels to go hang out with person 1, it takes them 5 seconds to do it. What is their velocity? The answer to that question would be negative 5.5 meters per second, or better, 5.5 meters per second to the left. That's their velocity. If I ask you for their speed, the answer is 11 meters per second, full stop. You see the distinction? So these two terms are related. Please, please, please be careful, because I will very frequently phrase my questions in such a way that it requires you know the difference. Because sometimes, as you'll see here in a minute, it can be less than obvious. All right, we got one more kinematic term we're going to have to learn. And this is probably the one that students are going to have the most amount of trouble with. And the reason they have a problem with it is because you spent your entire lives watching things move around. And usually when you see a thing move past you, you look at it and your brain immediately says, oh, that thing's going fast, or oh, that thing's going slow. So you've got a super easy handle on fast versus slow. That makes conceptual sense to most students without any extra work from us. So velocity and speed, that's easy to get your head around. But it turns out that to really understand what's going on, we're going to have to look even more closely. And it's not going to simply be enough to ask yourself whether something's going fast or slow. We're going to have to look instead at something called acceleration. And this is the part that often kind of blows students' minds a little bit, right? We're going to define this term acceleration in a very similar fashion to how we define velocity. It's a rate of change. But instead of being the rate that somebody's position is changing, acceleration is going to be the rate of change in their velocity. So how will we define that? Well, rate of change is always something over something, right? So we would say that your acceleration is going to be however much the velocity has changed by, divided by the time over which that velocity has changed. Does that make sense? What would the units of acceleration be? Well,
Meter per second?
not quite. Because remember, velocity is meters per second, right? So the numerator of this fraction is meters per second. But then I'm dividing it by a time, so it's meters per second per second. Which,
meter per second square?
That's right. So we would measure accelerations in meters per second squared. And that alone tends to sometimes blow students' minds a little bit. It's often easier to wrap your head around if you think about this as being just another way of writing this. It's meters per second per second. So imagine I have an object, and that object has an acceleration of 2 meters per second squared. What that means is that their velocity is changing by 2 meters per second every second. So if when I originally look at them, they've got a velocity of 0, but their acceleration is 2, then 1 second later, their velocity won't be 0 anymore. It will have gone up by 2, and now they've got a velocity of 2. So they're going faster than they used to. 1 second after that, their velocity will have changed even more. It'll have gone up by another 2. So 2 seconds later, they'll have a velocity of 4. 3 seconds later, they'll have a velocity of 6, then 8, then 10. Every second that passes, their velocity will change by positive 2. That's what it means to have an acceleration. And you'll notice what that means is that if their velocity is going up by 2 every second, that means that over time they're going faster and faster and faster and faster. So you can think of acceleration as being related to speeding up and slowing down. Make sense? Now, what about signs? Would it make sense for an acceleration to be negative? Could I have a negative acceleration?
Yes.
Absolutely. What might that represent?
Slow. I'm thinking like slowing down. We're slowing
Yeah,
down.
I mean, obviously, if I have a velocity of 0 and my acceleration was positive 2, then a second later my velocity is 2. Then after that it's 4, then 6. So that would clearly represent somebody speeding up. But imagine that I started with a velocity of 10, and I had an acceleration of -2. So at first they're going 10 meters per second. 1 second later, their velocity is 8. They're slower than they used to be. 1 second after that, it's 6, then 4, then 2. So that's somebody who is slowing down over time. Now, unfortunately, this leads me to a place where students often make a mistake because they sometimes get it in their heads that positive acceleration means speeding up and negative acceleration means slowing down. And that is not true. It's more complicated than that. And in order for me to demonstrate that, let me switch my screen share to something different. No, not the camera, stupid. There we go. All right, so where's my guy? There's my guy. All right, can you guys see this guy?
Yes.
All right, so what's going to happen is I've got this little guy here, and I can control his position, his velocity, and his acceleration any way I want. If I wanted to, right now, I've chosen a frame of reference, and you can see that my frame of reference has x equals 0 being right here in the middle of the screen. So I have him at position 0, but if I wanted to, I could be like, let's move to position 5. And it just moves him to that location. So I can change where he is. I can change what his velocity is. I can change what his acceleration is. Let's start him off at position 0. And let's give him a starting velocity of 0, but let's give him a positive acceleration, an acceleration of 1. So you'll notice what's going to happen is when I hit that and let it go, okay, that's annoying. The control bars for the zoom window were on top of the play button, so I couldn't hit the play button. Here we go. So we're going to hit the play button, and you can see that what happens is dude starts traveling, and let's pause it for a second. You notice now, a few seconds later, he's at a position that's no longer 0. Guys, shut up. Sorry for my dogs. They're very obnoxious. My wife just got home. He's got a velocity that's positive, so he's traveling to the right. And as time goes on, his velocity is getting bigger and bigger and bigger. Of course, he runs into this wall and stops abruptly. So that's what ended that whole thing. So clearly in that case, having a positive acceleration resulted in him speeding up. But what if I did the same thing, but I gave him a negative acceleration? Well, he's starting at x equals 0. He's got a velocity of 0, and now he's traveling to the left, but you'll notice he's going faster and faster as he goes. So he had a negative acceleration, and yet he was still speeding up. So the minus sign doesn't necessarily mean slowing down. It could be speeding up, depending on your circumstances. Let's try this example. All right, I'm going to start off with this guy. Let's kill this wall because I don't want him to hit the wall. Let's start him off over here at the house. I'm going to start him at position 8. I'm going to start him off. Actually, no, I'll start him with the tree. I'll start him at position -8. So I'm starting off the guy over by the tree. I'm going to give him a velocity of +5, but I'm going to give him an acceleration of -1. What's going to happen? Well, as time goes on, you'll notice he's moving to the right. I've paused it. His negative acceleration means that he's slowing down. He started off with a velocity of 5, but as he slows down, his velocity is getting smaller. So at first, negative acceleration does mean he's slowing down. But wait, look what happens. Oh no! At some point, the guy turned around, right? His velocity got so small, it passed through zero and turned negative. And now he's got a negative velocity and a negative acceleration. And notice what's happening to his velocity. It's getting larger and larger and larger over time. So if I've got a negative velocity and a negative acceleration, it means that I'm speeding up. If I have a positive velocity and a positive acceleration, it means that I'm speeding up. But if I have a positive velocity and a negative acceleration, if they're in opposite directions, I'm slowing down. So the key insight here is that acceleration has a sign, but you speed up when your acceleration and velocity both have the same sign, and you slow down when your acceleration and velocity have opposite signs. Does that make sense? There's still a direction associated with it. Here I can use little arrows to represent the velocity. Let's give this guy a velocity of like 10. And you can see that this red arrow represents the size of his velocity. He's got a velocity of 10, so I've got a big red arrow to the right because it's positive 10. I'm going to give him an acceleration of -2 and click on the acceleration vector. The acceleration vector is in the opposite direction. It's to the left. And because they're in opposite directions, as time goes on, well, that didn't work. I'd love to be able to do this in like slower increments. Let's make his velocity be a little bit slower. Let's make it be +4 and -2 so that he doesn't shoot off screen before I'm ready for him to. So you'll notice that what's going to happen is that little red velocity vector, as time goes on, is going to get shorter and shorter and shorter. And at some point, it reaches 0 and turns negative. And now that red velocity vector is going to get bigger and bigger and bigger, going to the left. So that's the concept of acceleration. It's about having a velocity that changes with time. Notice if I have a velocity of, let's say 5, but an acceleration, let's go down to 2. Velocity of 2 and an acceleration of 0, all that means is that as time passes, my velocity stays constant. It's not changing at all until I hit the wall and stop abruptly. Does that make sense?
Yes.
So that's this concept of acceleration. It's about the rate of change in an object's velocity. Having an acceleration of 0 suggests that your velocity, whatever it is not changing from moment to moment. Having a velocity that's positive means you're either speeding up or slowing down. Having a velocity that's negative is either speeding up or slowing down. And which of those it is depends on whether your velocity is the same sign or the opposite sign of your acceleration. Same sign, speeding up. Opposite signs, you're slowing down. And once you sort of get this sort of wrapped around in your head, everything else is going to fall into place. Let's make it more complicated. Let's consider for a moment I've got a race car driving on a circular track. And this guy is going to go around the track in a counterclockwise direction. And the entire time that he drives around this circular loop, I'm looking at his speedometer, and I see that his speedometer reads the entire time 50 miles per hour. And it's pegged at 50 the entire lap. Is it fair to say that this person is accelerating?
No, because his speed is constant.
Ah, so remember how I said velocity and speed are two different things? They're related, but not the same. Notice that the definition of acceleration is not the rate of change of speed, it's the rate of change of velocity. So, is this person driving around that circular track, is their velocity changing?
Yes.
Yes, it is. So, what's going to happen is this person has a velocity that's changing. The speed may be 50 the entire time, but up here, it's 50 miles per hour to the right. But halfway around the track, he's traveling the exact opposite direction. Here, it's 50 miles per hour to the left. So clearly, it has changed. So what's going to happen is this person, even if you drive around a track at a constant speed, they are accelerating. And I want to make that point because what's going to happen is when we talk about acceleration, we often think acceleration means speeding up and slowing down. But it's even then more complicated than that because you could be speeding up, you could be slowing down, but you could also be changing direction. So any of those three things are going to be a form of acceleration, speeding up, slowing down, or changing direction. Now, this part right here, we're not going to deal with for a few more chapters. What's going to happen is in chapter 3, we'll learn how to deal with things that aren't traveling in straight lines. In chapter 6, we'll deal specifically with the problem of things going around in circles. And we'll learn how to calculate how much acceleration there is, in this case, in chapter 6. Chapter 2, we're going to restrict ourselves to stuff traveling in nice, simple, straight lines. And if I'm traveling in a straight line, changing direction, at least turning left and right, is not an option. And in that case, acceleration really will be just speeding up or slowing down. But I wanted to make sure that you guys were aware going in that eventually we'll expand what it means to accelerate to include turning left and right or up or down rather than just straight line motion. And it's going to be a bit more complicated. So how are we doing so far? That pretty sensible? All right. So we've got our base vocabulary set. We know what all the terms, thanks for the thumbs up, that's helpful. Yeah, bear in mind, guys, I'm used to talking to like a group full of students, and I tend to teach by asking lots of questions. So, you know, I get that sometimes you guys got stuff going on at home or you got microphone issues and talking doesn't necessarily help, but it really will help me to get some degree of feedback. It helps with pacing. So even the thumbs up on the chat window helps me to know that I'm connecting. So please, feedback is great. If you've got questions, you know, don't hesitate to type questions in the chat. I'll answer them there. But the more feedback you give me, the more we're going to get out of this this process. All right. So what we need to do now is we need to figure out how all these things fit together. And to make some sort of sense of like how to mathematically approach all this stuff. But it's complicated. And one way to think about how it's complicated is to imagine a couple of scenarios. So imagine that I tell you that I'm going to get in my car and I'm going to take a trip. And let's make things simple by assuming this trip is nice and happy and in a simple straight line. And I'm going to take a trip and drive a distance of 120 miles. And it takes me 2 hours to make that trip. So here's my nice happy straight line. Here's my house where I start. Here's the place where I'm going. I'm traveling 120 miles, and the entire trip took me 2 hours. What was my velocity for that trip?
Okay, I don't think so I'm right, but 120 divided by 126 minute,
Why 126 minutes?
like hour need to be changed to second. Hold on a second.
Well, you could. If you wanted to have miles per second, you could totally do it that way. But remember, we can work in whatever units we're comfortable with. And my
Okay.
speedometer reads miles per hour. So let's just stick with hours.
Okay, it will be like 60 miles per hour.
Yeah. So if I take 120 miles divided by 2 hours, that's 60 miles per hour, which is not an unreasonable speed to be driving down the interstate. Now, here's the problem. I can almost guarantee you that during that trip, my speedometer probably said things different from 60 along the course of that trip. There were probably places during that trip where I was at a stop sign and my speedometer read 0. And there's probably sections during that trip where I'm on the interstate and there's no way I'm driving only 60 miles an hour on the interstate. That's crazy, right? Which begs the question, what the heck does that number even represent? If my speedometer was sometimes 0 and other times, I don't know, 70 or 80, what does this number even represent?
Is it
Velocity?
Well, the number we got was 60, but I'm trying to figure out like why do we get a number of 60 when my speedometer didn't necessarily say 60? I was probably driving 70 on the interstate and probably driving 0 when I was stopped at red lights.
Is it like the average of the speed of the trip?
Yeah, and in fact, that's what we're going to call this. We're going to call this the average velocity. Right? And the average velocity is exactly what we've been saying it is. It's how far I went, my total displacement divided by the total time. The problem, though, is that in many cases, the average velocity and the velocity that my speedometer is reading, my instantaneous velocity, might be something different. There may be times when I was traveling faster than the average velocity. They're being counterbalanced by times where I was going slower than the average velocity, and the average velocity is somewhere in between. It's kind of like how when I calculate your average for your grade at the end of the semester, if there were some assignments you got 100 on, and there were other assignments you got a 70 on, then your total class grade is going to be less than 100, but more than 70, somewhere in between, right? That's the idea. Now, here's where students go wrong. Let's make this problem a bit more complex and see if we know how to adjust for it. So what if I tell you that I'm going to travel this whole 120 miles, but what's going to happen is I'm going to travel 50 miles of that 120, and during that time, the speedometer is going to read 40 miles per hour for that entire leg of the trip, right? Then what's going to happen is I'm going to stop for lunch. And I'm going to stop for 20 minutes. Then I'm going to take off again, and I'm going to drive the last 70 miles. But I want to make up for going super slow, and I'm going to drive that last 70 miles at a speed of 80 miles per hour. Got it? So part of the trip I'm going 40, part of the trip I'm going 0, part of the trip I'm going 80. I want to find my average velocity for that entire trip.
So would you do the 50 over 40, the 0 over 20, and the 70 over 80, and then use those to find the average?
Not quite. When I ask this question, I often see people try a bunch of ways that are wrong to start with. One of the most common ways I see people do this is they hear the word average, and of course, when you hear the word average, what do you normally think? You think add up all the numbers and divide by how many numbers you've got, right?
Yeah.
So if I was to do that, what numbers would I be doing? Well, I had a speed of 40, a speed of 0, right? Because when I'm stopped, my velocity is 0. And then speed of 80. So 40 plus 80 plus 0 is 120 divided by 3. That's not right. That gives me a number, but it's not the number that I want.
Okay.
So, when you can do average velocities, it's not just take all the velocities and average them. That's not how it works. It's the same way that when I calculate your grade at the end of the semester, I don't just take all the grades you got and average those numbers, because some of those assignments are worth more than other assignments, right? If you got 100 on the final exam, but you got a 0 on some piddly little quiz, that quiz doesn't bring you down nearly as much as that final exam brings you up. So that wouldn't be an average of 50 in the middle. It'd be closer to 100 than it would be to 0. And to do this, we got to go back to the definition of average velocity. It's how far you went divided by how much time it took. So if I want to find the average velocity for this trip, how far did I go? What is the delta x for this trip?
120.
Yeah, it's still 120, right? I went 120 miles. So the delta x part is 120 miles. Now, how long did this trip take me?
2 hours.
Are you sure?
No, 2 hours and 20 minutes.
Not necessarily, because wait a second. For the first part of the trip, I told you how far I went for that one part of the trip, and I told you the speed during that part of the trip. I didn't tell you the time. I have no idea how long it took to drive that 50 miles. But if I wanted to know, how would I do it?
Well, you stopped for 20 minutes, so wouldn't that play a part?
It absolutely will, and we'll get to that. But
so velocity need to be divided by, to get that, we have to calculate for the hours from a 40.
Yeah. So what's going to happen is I'm going to take this trip and break it up into 3 sections. And I'm going to think about the 3 sections separately for a minute. So forget these parts. Ignore them. Do them last. For this first part of the trip, I had one speed the whole time, and I traveled one distance the whole way. So I can use this same formula for just that part of the trip. And let me take out a clean sheet here. So if I have V equals delta X over delta T, and I know that during the first section of the trip, the V was 40 miles per hour. The delta X was 50 miles. And the delta T was, I don't know. I can solve that for delta T. I'll multiply delta T on this side. These two things will swap places, basically. So delta T is going to equal 50 miles divided by 40 miles per hour, right? So 50 divided by 40 is going to be 1.25. I don't know why I pulled the calculator out when I did it in my head, but whatever. So far, so good?
Yes.
So just to go this section of the trip, it took me an amount of time of 1.25 hours, 1 hour and 15 minutes just to do this part of the trip. Now, this part of the trip is easy. I just flat out told you it took 20 minutes, right? That's a third of an hour. So right now, for my total trip, I've got 1.25 hours, 1/3, that's 0.333 hours for the stop. So it will play a part. And then for this part here, what would that be? Same deal, right? Except now it'll be 70 miles divided by, what we say it was 80 miles per hour. That part of the trip went way quicker. Right. So notice I went further during that section of the trip, but in less time because I was driving way faster. So now, if I want to find my average velocity for the whole trip, I'll take the distance for the whole trip, which was the total number of miles, 120, divided by the total time, which is going to be 1.25 hours plus 0.333 hours plus 0.875 hours.
I'm sorry. Can you show the other sheet one more time? I'm sorry.
So there, I'm just figuring out for each section of the trip, the delta t for the first section of the trip, I just took that speed divided by that speed, or that distance divided by that speed, gave me that time. For the third section of the trip, it was that distance divided by this speed, got that time. Right?
Okay. Okay. Sorry, I was trying to catch up.
No, you're cool. You're cool. And like if I'm going quickly, that's don't be afraid to stop me because sometimes I'm going quick. You with me? Everybody on the same page?
Yes, I'm good now.
Okay.
Thank you.
So now we go back to this. I want to find my average velocity for the whole trip. It's the total distance divided by the total amount of time. So what is that? 1.25 plus 0.333 plus
2.458.
all right, 120 divided by yada yada yada. I get 49.3 miles per hour. So one thing you'll notice, if I had just gone and averaged all my three velocities, I would not have gotten this answer. Notice my answer is a lot closer to 40 miles per hour than it is to 80 miles per hour. How come?
Can you repeat the question one more time? Sorry.
Yeah, so I did the average velocity for the whole trip, and I got a number of 49.3, right? That 49.3 is pretty close to 40, and it's pretty far from 80. But why is it so much closer to 40 than it is to 80?
Because there's a time we stopped.
Part of it is that. Part of it is that this time when I'm stopping is counting against me. The other reason is because I'm spending way more time going slow than I am going fast. So in a way, the more time that I take at that lower speed, the more it's counting toward my average. What if I changed the question and made it simpler, right? What if instead I eliminate the stop for lunch completely? I don't stop for 20 minutes. And I'm going to drive 40 miles per hour for 1 hour. And then I'm going to drive 80 miles per hour for also 1 hour. What's my average velocity? Take a crack at that one and see if you can get that one before I tell you. We're going to follow this up with a secondary question. We're going to go 40 miles per hour for 2 hours and 80 miles per hour still for 1 hour. And I'm curious how the average velocities for these two questions are going to be different. So how would I do that? Well, what's the definition of average velocity? It's how far you went divided by how much time it took. Now, this question is framed differently than the previous one because here I gave you for both sections how fast and how long. I didn't tell you how far. Whereas previously I told you how far and you had to figure out how long. So if I drive 40 miles an hour for 1 hour, how far did I go?
Technically, you're gonna divide it by you cancel out the hours and then you divide it by 40 divided by 1. It's 40 miles.
Yeah, duh. If you drive 40 miles per hour for 1 hour, you're gonna go 40 miles. That's, kind of a no-brainer. So obviously here I went a distance of 40 miles. And over here I went a distance of obviously 80 miles. That's a no-brainer. So when I'm doing the average velocity, my total distance is going to be 40 plus 80. It's 120. All right. How long did it take?
2 hours.
2 hours. And notice (120 divided by 2 is 60. I get 60 miles per hour. And you'll notice if I had just gone and done the obvious but wrong thing and taken 40 and 80 and averaged them, well, 40 plus 80 divided by 2 is 60. So if I spend the same time at each of those speeds, my average velocity will literally be the average of my velocities. But what if I take different amounts of time at those different speeds? Like in this problem, it won't be that simple anymore. Because now what's going to happen is if I go 40 miles an hour for 2 hours, I'm not going to go 40 miles. I'm going to travel 80 miles, right? If I go 80 miles an hour for 1 hour, I'm still going to go another 80 miles. So for this one, my average velocity is going to be my total difference, distance, which is not 120 anymore. It's 160. And it's going to take me not 2 hours, but 3 hours. And 160 divided by 3
53.
is 53.3 mph. Notice my average velocity was closer to 40 than it was to 80. Why? Because I spent more time going slow and less time going fast. So my average velocity was closer to my slow speed and further away from the high speed. So I can't just take the average of 40 and 80. That won't work because I'm spending different times at both of those velocities. So now that we know how to find an average velocity, it probably would behoove me to ask, what does that average velocity even represent? Like I have a number, but it doesn't necessarily coincide with what my speedometer says, because during this trip, my speedometer said this some of the time and this some of the rest of the time. So what's that 53.3 even represent? And one way you can think about these average quantities is your average velocity is the velocity you would have to travel that distance in that amount of time if you only ever had one velocity the entire way. In other words, if I drive 40 miles an hour for an hour, 80 miles an hour for an hour, I'm going to end up 120 miles away, and it's going to take me 2 hours to get there. But what if instead I just drove one speed the whole time? What if I drove 60 miles an hour the whole time? Well, 2 hours later, I would be 120 miles away. I'd get the same distance in the same amount of time going this one speed that I would going this combination of two speeds. Does that make sense?
So you mean like we have to have like the same time to use the average rather than different
Right.
time.
If I have if I have two different velocities, but I have those velocities for the same amount of time, they're both contributing the same amount to my average velocity. And what will happen is this number literally was the average of those two numbers, but that only worked because the times were the same. 9 times out of 10, that won't work. So you shouldn't just average those. You have to figure out how far did you go and how much time did it take. Because the definition of average velocity is distance over time. So go back to basics. Don't just average the numbers, because that's usually going to give you the wrong answer. It's only going to give you the right answer in very, very specific special cases.
Okay.
Yeah. But that average velocity represents, like, if I only had one speed the whole way, this is the speed that it would have had to have been. That's the way to think about that. Just like if I, if you had 2 students and I had one student who got 100 on a bunch of assignments and zeros on a bunch of other assignments, and it averaged out to 70, they would get the exact same grade at the end of the semester as another student who only ever got 70s on every assignment, right? They would both end up with the exact same grade. That's the idea. Okay, so we have this concept of average velocity kind of locked down, but what we really are going to care about most of the time is not your average velocity. We usually care about what your speedometer says. We care about what we call the instantaneous velocity. And so we're going to have to get a handle on what that even means. What is my velocity telling me if it's not telling me these numbers? And in order to wrap that concept up, what I like to do is graphs. So let's consider the following scenario. All right, I'm going to plot the position of an object as a function of time. So here is where the dude is. This is the amount of time that's passed. Let's have the object start at a position of 0. And let's start simple. Let's have that be my position as a function of time graph. Describe to me what that object is doing.
It goes linear.
Yeah, but like in words, like if I were describing what the dude was doing, what would that look like?
His time and his distance are the same.
Right, but I like if I was describing to my 5-year-old nephew what I was seeing, what would I be telling him? Look, I just opened like 3 copies of this thing.
He's going, like he doesn't stop.
He's definitely not stopping. That's definitely correct. So what I'm going to do, I'm going to go back to my little moving man, and I'm going to make a graph that looks just like this with the moving man. So here's my little dude. Hang on, let me share that screen. So here's my little dude. And I'm going to start him at time 0 on my graph. I had him at position 0. So I'm going to have him start at position 0. And I'm going to give him a velocity of, let's say, 2. And I'm going to hit start. And he's going to go shooting off and travel to the right at a speed of 2 the entire time. Now, if I want to do a chart of what that looks like, let's do the same thing. Here's my dude. And here's a bunch of charts. And what I'm going to be looking at is a graph of his position. Now watch this. I'm going to make his velocity be 2. And watch this graph right here. This is where his position is. Take that wall away. Hit the button. And look. The graph that I got is exactly the graph that I was drawing a second ago, right? It was linear. So in words, if I was describing what the position of that guy was doing or what I was seeing, I'm seeing him travel to the right at a speed that wasn't changing. He had a speed of 2 the entire way. Does that make sense? What would happen? How would my graph be different if his speed wasn't 2, but it was 1 instead? What would look different on that graph?
It doesn't have a much different, but the speed will be reduced.
So on the graph, how would the graph look different?
It's not gonna make any difference except the speed.
Okay, so let's do the experiment. Let's go back, and I'm gonna make this with a speed of 2, and we see this graph. And I wish I could keep this graph up while the second one shows, but I can't. So remember what this looks like.
Okay.
Right? Now let's reset it. I'm going to change that speed to only 1, and you're going to tell me what that graph looks, how that graph looks different.
It's gonna shift it to 1. Oh wow.
So how is that graph different from the first graph?
It's more toward to the x-axis rather than the y-axis.
Yeah, it's not as steep, right? The previous graph, if you recall, the first time we did it, the graph was like steeper, right?
Mm-hmm.
And what's going to happen is if I did it even slower, if I drop that down to like 0.5, it would have, I can't draw a straight line to save my life, dude. It would have been shallower. So what's happening is when we do these sorts of graphs, the velocity ends up being the slope of that graph. Just think about it. What's the slope? What's the definition of the word slope?
Rise over run.
Rise over run. Well, if I'm going back and I'm looking at my hand-drawn graph here, the rise of this graph is going to be how much x has changed. The rise would be the change in x. The run would be the change in time. Oh, look, delta x over delta t, that's the definition of the velocity. So the slope of that graph tells me the velocity. If I have a slope that is steeper, this has a higher velocity. This is a lower velocity. Right? So the shape of that graph conveys information about the speed. It conveys information about the velocity. Let's make it more complicated. What if I've got a graph of position versus time, only it looks something like this? What the heck? What am I looking at here? What am I seeing?
First,
Oh, go ahead. Sorry.
go ahead. It's okay. Go ahead.
No, I was gonna say, can I see the first one again? I'm sorry. I was drawing it when you changed it.
Oh yeah, no problem. So originally we just had one dude going one speed the whole time. So I had a straight line, and the steeper the line, the bigger the slope. So the steeper it was, the faster I'm going. The shallower it was, the slower I was going.
So
Does that make sense?
steeper.
Yeah.
I'm sorry. Say that part again.
So remember back when you did algebra and you learned about slopes? The definition of slope was rise
Yeah.
over run. So what was going to happen is you learn stuff in algebra class. Like if you had a line on a graph and it was super, super steep, right? This was a positive slope, right? And the bigger the slope, the bigger the number, that was the larger rise for the amount of run. So that would be a large slope, and a shallow slope would be not as steep. They're both positive, but this would be a big number. That'd be a small number. By comparison, if you had a graph that looked like this, that was a negative slope, right?
Yeah.
Because the rise was negative, the run was positive. So that gave you a negative slope. And the steeper it was there, like this would be a big steep number. this would be a smaller slope. So this would be a low V,
Mm-hmm.
and this would be fast but negative. And if you had a graph that looked like this was a slope of what?
0.
That's right. If you had a graph that looked like this, what was the slope of that?
There is none.
That's right. It's undefined.
Yeah, okay, undefined.
In physics, an undefined slope is often like infinity.
Okay.
It's because we have a rise of a lot over a run of 0. So it's like dividing by 0. That's why it's undefined. Does that make sense?
Yeah.
So that's all junk that you guys learned back in algebra class a million, zillion, gazillion years ago. I want to use that idea to figure out what's happening in this graph. I want to break down that graph, thinking about it in terms of slope. So you can see that what's happening is during this section of the graph, that's a straight line. It's got one slope, and it's a positive slope. So this is an object with a positive velocity. All right. Then during this section of the graph, what's my slope? It's 0, right?
Yes.
So this is, maybe I'm starting at my house and I'm traveling at one speed away from my house. And then right here, what's happening?
Stops. You maybe stopped.
Yeah, I'm stopped. I'm at a stop sign or something. Then right here, what's happening?
You're going fast.
I'm going
You're going
fast,
down.
but something else has changed too.
You're going direct. You change the direction to negative.
Yes. So over here, maybe I was traveling away from my house, but maybe here I've turned around and I'm traveling back to the house.
Mm-hmm.
Right? And then notice when I get right here, I'm at x equals 0. I'm at the same place I started. So maybe this is me leaving the house, getting to a stop sign, stopping, realizing, oh crap, I forgot my stuff. I need to go back to the house. Boom. Then I'm traveling away from the house again. What happens right here?
You increase your speed.
Is that right? You're close. It is about speed.
Mm,
You change your direction as well.
Here or here?
The bottom, you increasing your speed.
Yeah, right here I've got, well, I have one speed because this is a straight line. So it's one speed the entire way. But then right here, something changes because my slope becomes way less steep all of a sudden. So during this section, I'm not going as fast as I was during this section. So maybe I'm speeding and then I see a cop and I slow down.
Okay.
Right. So this is me traveling slow. This is me traveling fast. So I can get all kinds of information from the size and the shape of this graph. And what's going to happen is my speedometer during this trip is going to say a whole bunch of different stuff. I'm going to have many different velocities along the way. My average velocity, however, would be the velocity I'd have to get from point A to point B if I could only ever have one slope the entire time. My average velocity would be the slope of that line right there. If I could only have one slope the whole way, that would be it. Does that make sense?
Yes.
All right. So I think it's gonna be where we stop for today. Tomorrow during lab, which I'm gonna meet at 1 o'clock, we're gonna play around with some stuff like this, and we're gonna do some graphy stuff. But this should prepare you to do that. So far, so good?
Yes. I have a quick question. We have something due today, right? At 3 o'clock?
I'll double check. I don't recall what was that. That may have been
it
an
was
error.
the sig. It was the units and sig figs.
Okay, no, that's going to get changed. That's the pre-lab for tomorrow's lab.
Mm-hmm.
When I imported the stuff from the previous year, it gave some automatic dates, and they didn't all translate perfectly, so I'll have to adjust those. So it's not really due today.
Okay, perfect.
And I've had several people who've already turned it in, and they're going to want to turn it in again because I've already looked at those, and several of them have gotten all the stuff wrong because they haven't had the lesson on that stuff yet. So yeah, it's not due today. It'll be at the end of the day tomorrow.
Okay, thank you.
You're welcome, guys. All right. Anything else?
That's pretty much it. Thank you.
Oh, you're very welcome, folks. Have a good day, and I will talk to you later.